Welcome to the Explainer. Today, we're unpacking a seriously disruptive new research paper called AgentArk. Right now, the industry is burning through massive amounts of compute and, frankly, millions of dollars, trying to get teams of AI agents to just work together. But this paper asks a pretty radical question. What if we could take all of that messy collective intelligence and just cram it into the brain of one hyper-efficient model? Okay, let's dive into this. The AI world has this massive obsession with agent teams right now, and I get it. The pitch sounds completely irresistible. Instead of one AI doing a task, you deploy an entire squad, right? You've got a researcher agent, a coder agent, a reviewer agent, all debating and collaborating to find the perfect solution. But recent evaluations reveal a much harsher reality. As the research puts it, multi-agent AI systems are a compelling idea with a notoriously poor track record on most real-world tasks. The hype is basically severely outpacing the actual results when you take them out of the lab. And this brilliantly illustrates that exact point. The numbers paint a pretty stark picture here. In systematic evaluations, a squad of debating agents actually lost to a simple single agent on 5 out of 9 major benchmarks. And worse, they required an absolute fortune in compute power just to achieve those subpar results. So forcing language models to debate on the fly, it just isn't the silver bullet we all kind of hoped it was. So here is our roadmap for today. We'll unpack the multi-agent illusion, explore the AgentArk paradigm shift, break down their 3 pillars of distillation, look at the proof in the data, and finally discuss what this all means for the future of efficient AI. Let's get into it. Starting with Section 1, the multi-agent illusion and the inference time bottleneck. Why exactly are these agent teams failing when it matters most? Well, the core issue here is that these agents are essentially forced to improvise on stage at test time. The computational overhead is just enormous. Because every single agent has to process every other agent's output, the cost grows quadratically. If you have 5 agents, it's not just 5 times the work. It's a tangled, massive web of API calls and token generation. It's literally a logistical nightmare. Plus, we see this weird phenomenon called sycophancy. Instead of reasoning independently, agents just kind of agree with each other way too quickly to please the system, leading to premature consensus on totally wrong answers. Competition actually degrades their performance. And if one agent hallucinates a fact, that error often doesn't get corrected. It actually amplifies across the whole group, creating this highly confident collective false memory. Moving to Section 2, the AgentArk paradigm shift and shifting the compute. The researchers behind AgentArk asked a really brilliant question. What if we could shift all that heavy lifting to the training phase? The old method relies entirely on inference time compute. You're paying for high latency and on-the-fly debate every single time you ask the AI a question. Think of it like taking a stressful open-book group test where everyone is actively arguing about the answer while the clock is ticking down. AgentArk totally flips the script to training time compute. It forces the model to undergo rigorous solo studying and rehearsal offline, internalizing that entire debate process. So by the time you actually deploy it, the single agent arrives perfectly prepared, delivering low-latency, highly optimized answers in a single, confident forward pass. Which brings us to Section 3, the 3 pillars of distillation, or exactly how AgentArk works. So how do we fix this? Let's look at their 3-step framework. AgentArk doesn't just copy the final answers from the agent team. It extracts the knowledge through 3 progressively deeper nested layers of distillation. We've got reasoning-enhanced supervised fine-tuning, trajectory-based data augmentation, and process-aware distillation. Let's break these down to see how they successfully shift explicit multi-agent dynamics into implicit single-model capabilities. Let's see how this builds, starting with Step 1, RSFT. Usually, distillation just teaches a smaller student model to memorize a final answer provided by a larger teacher model, but AgentArk's RSFT goes much deeper. It trains the student on the intermediate reasoning trajectories that the agent group actually used to reach that consensus. It basically teaches the single agent the underlying structural consistency of a multi-agent reasoning path, making absolutely sure it can reliably string together a logical sequence of intermediate steps before ever blurting out an answer. Step 2 is data augmentation. The researchers realized that just showing the model one successful path, that isn't enough, so they inject diverse reasoning chains, and crucially, corrective traces. This means they feed the student model examples where a teacher agent actually made a mistake, got a harsh critique from another agent, and then successfully pivoted to the correct answer. Imagine learning not just how to solve a complex math problem, but exactly how to catch yourself when you accidentally carry the one incorrectly. By studying these diverse logs, the single model learns how to recover from its own mistakes all within a single thought process. And the final step is the engine room's most advanced pillar, process-aware distillation, or PAD. This is where the true magic happens. Here, they use a process reward model to provide step-level rewards during training. Normally, reward models just look at the finish line, right? Is the final answer right or wrong? But a process reward model looks at the AI's internal scratch pad. It grades the agent's thought process step by step. If step 1 is a brilliant logical deduction, it gets heavily rewarded, even if the final answer ends up slightly off later on. This intricately trains the agent to internalize the critique and revision dynamics of a full debate. It perfectly emulates dialectical reasoning, literally arguing with itself and self-checking, all without ever needing to consult a second agent. Moving on to Section 4, the proof in the data, and validating the theory. Let's see if it actually worked. When we look at multimodal distillation across the GSMAK math benchmark and the MED-MCQA medical benchmark, the results are crystal clear. All three of these reasoning-centric methods boost the overall performance of the single agent. But PAD, that process-aware distillation we just talked about, shows exceptionally robust and stable gains across these entirely different task domains. It allows the single model to emulate complex multi-agent behavior with incredible accuracy, whether it's solving geometry or diagnosing a patient. Now, what's really interesting about this next point is how it proves the importance of reasoning quality over quantity as training data scales. While simply injecting more and more augmented data causes performance to eventually spike and then degrade, PAD maintains stable, climbing gains. The research found that blindly throwing more reasoning trajectories into the training data doesn't reliably improve performance. Instead, PAD's high-signal step-by-step process supervision yields the most robust scaling behaviors. So you don't need infinite data. You just need deeply evaluated data. But there is a catch here, and it's directly tied to model size. The researchers discovered what they call a critical cognitive capacity threshold. If you try to distill multi-agent intelligence into an ultra-small model, say a 0.6 billion parameter model, the gains are strictly bounded. It's like trying to fit a university-level debate into a middle school textbook. The small model just doesn't have the synaptic space to balance these new, complex reasoning patterns with its foundational knowledge base. It actually starts to forget things. But once you move up to mid-size models, like 1.7 billion parameters and above, they finally have sufficient cognitive capacity to fully absorb and utilize this distilled collective wisdom without degrading. Finally, Section 5, the future of efficient AI, looking at the horizon and the broader implications. So what does this all mean? Well, what AgentArk ultimately proves is a massive economic and functional shift for the industry. By trading increased computation during training, we unlock massive, low-latency savings at deployment. And because this distillation method is algorithm-agnostic, it generalizes across entirely diverse tasks. This means we can suddenly run complex, agentic-level reasoning on resource-constrained edge devices, literally like the phone in your pocket. Furthermore, by keeping the reasoning internal to one single model, it vastly reduces the collective failures, the sycophancy, and those amplified hallucinations that currently plague live multi-agent debates. We'll end on this thought. The industry is currently rushing to build sprawling, expensive networks of specialized agents. But based on the AgentArk framework, we really have to ask, are teams of agents actually the future of deployment? Or is the ultimate team just one perfectly distilled, rigorously rehearsed super agent? It's a profound shift in how we think about scaling AI intelligence, and it suggests that the most efficient way forward might just be a return to the power of one. Thanks for joining this explainer. We'll see you next time.